I'm going to talk a little bit about quantum angular momentum in quantum mechanics. This applies for rotation. It also applies for orbital angular momentum. It applies for just about any angular momentum in quantum mechanics. So starting off classically, we've talked about angular momentum. L is equal to R cross P. We can express that, if we will, as a determinant of a 3x3 matrix where I have my I, J, and K unit vectors, the X, Y, Z coordinates, and then coordinates for momentum, Px, Py, Pz. And so what we're going to end up with is the angular momentum vector is going to be a Lx quantity times the I unit vector plus Ly times J unit vector, Y direction, Lz, K unit vector, Z direction. We can also show that these terms here are ypz minus zpy, etc., etc. If I do this quantum mechanically now, momentum is going to be I minus IH bar times the partial derivative. And so I end up with Lx equal to IH bar y partial z minus c partial y instead of y pz minus zpy. Same thing for Ly and Lz. I can show that in Cartesian coordinates, I'm only going to do two, that L squared is equal to this collection here, and that the Z component is going to be just equal to the partial derivative of rotation about the Z axis. Okay. The magnitude of angular momentum in quantum mechanics is going to be, for L, is going to be some L plus 1 to the 1/2 h bar, where L goes from 0, 1, 2, 3, etc. The Z component is going to be equal to some additional quantum number m sub L times h bar, where m sub L varies from minus L to plus L in intervals of 1. Now you might ask, well, what about Lx and Ly? Can't I get, or Ms, My? The problem is that the three angular momentum operators, the components for angular momentum, do not commute. I have the commutator relationships put here, and so the commutator of Lx and Ly is IH bar Lz. What does that mean? When the components of the angular momentum vector don't commute with each other, it means that I can only measure one component. And L squared. So I can determine L squared, the angular momentum squared. I can determine the Z component of angular momentum. I can't determine X or Y, because if I do, I'll scramble the others. So now what I have here is basically an idea of showing that how can we represent this. I have this object rotating, and it can, imagine if this is the ML equals 2, 1, 0, minus 1, minus 2. This is for a L equals 2. And this sort of can rotate along, the angular momentum vector can rotate around the Z axis, just so that the Z component of angular momentum stays the same. So it's going to be somewhere in a cone. The same thing for 1 and 0, minus 1, minus 2. We can diagram this in another way here. If I look at it, so if I look at this end on, what I have here is this circle, which this circle has a radius. In this case, L equals 2. So it's going to have a radius of square root of 2 plus 1, h bar, or if you prefer, square root of 6 h bar, where the z components are going to be equal to h bar, 2h bar, minus h bar, actually 0h bar here, minus h bar, 2h bar, and then minus 2h bar. I have another diagram to the right which shows, sort of trying to show you that yes, these angular momentum vectors are somewhere in a cone. They can be anywhere along, just so long as they're a set distance away from the z-axis. Okay. Basic concept. This applies, that you should keep in mind, this is going to apply for any angular momentum, J, any generic angular momentum. It can be the angular momentum of rotation of a molecule. It can be the angular momentum of rotation of a electron in an orbit. It can be the nuclear spin. It can be electron spin. Any angular momentum is going to have a magnitude of h bar j plus 1 to the 1/2 and a z component of h bar m sub j. The last piece I wanted to talk about with the idea of angular momentum is that of spin. Electron spin or nuclear spin are concepts that have no real classical analog. An electron has an intrinsic angular momentum. Another way to look at it is that it has an intrinsic magnetic moment. So it's not really spinning, but the magnetic moment, what we have as an analog is that essentially, if we remember, a spinning charge generates a magnetic field along the axis of rotation. So the electron behaves as if it's spinning. Now, we can get half integer for nuclei. Actually, the electron, proton, and neutron are all spin 1/2 particles. When I put them together, I can get spin 0, spin 1, whatever we want. But these are, excuse me. So the same rule applies. S is a angular momentum, except that now S is equal to 1/2. That is intrinsic for every electron. If it's not spin 1/2, it's not an electron. So with that, the expectation value of spin squared to the 1/2 is just the magnitude is going to be h bar s plus 1 to the 1/2. In other words, h bar 1/2 3/2 square root or square root of 3/4 h bar. The z component is going to be ms h bar, which is going to be either, we call it up or down, is either plus or minus 1/2. And again, I'm showing this here. So it's going to be somewhere in this cone, or somewhere in this cone right here, because it has to have this fixed orientation to the z-axis.